In this video, I want to go over a Nastran tutorial for beginners. In this exercise, I want to show you how to configure a normal modes analysis, a statics, and a frequency response analysis. Now, this tutorial is assuming you have never performed a Nastran analysis. So I'm going to show you every step of the process. Here on the left, I have an agenda of what you can expect in this exercise. First, we are going to talk about units, and then I'll show you a very simple example where you mesh a plate, and then I'll start off with configuring a normal modes analysis. Normal modes analysis. This is of interest if you're in dynamics, but this is also very useful if you're a beginner in FEA. This analysis type is actually a very good debugging step when it comes to configuring a statics analysis. So that's why I wanted to start off with showing you how to configure a normal modes analysis. After that, we'll go ahead and switch over to a statics analysis, and then we'll end it off with a frequency response analysis. So whether you're only familiar with statics analysis or you are from the dynamics community, I want to make this tutorial as large as possible. I want to target a community as large as possible. Now, one other thing I'm going to do, I'm going to talk about a very common error that a lot of beginners have. This is known as user fatal message 9050. In newer versions of Nastran, it's called a user fatal message 10,030 and 10,031. So given that this is a very common error, I want to talk about what this error means and how to fix it when you're performing a statics analysis. Now, here is a brief description of the finite element model we are going to construct. This description has more details regarding how it's configured for a frequency response analysis. Feel free to pause the video and read this description. Here, I'll just briefly cover what the supports are and what the loading is. So on one edge of the plate, we're going to fully constrain it. We're going to apply a force at one of the corners, and then we're going to apply a pressure distribution to the entire plate. So again, feel free to pause the video and read more about the description of the analysis model. Okay, so like I said at the beginning of the video, this is a Nastran tutorial. One of the skills you're going to need when you use Nastran, you will need to be able to read the input file for Nastran. So basically what the input file is, here's a larger example. The input file contains all the nodes, all the elements, all the materials, all the loads and supports. It contains information about the load cases. Basically, your entire finite element model is contained in a text file. You then give this text file to Nastran. Nastran performs the analysis, and then it stores all the results in a different file. So in this video, what I'm going to show you how to build all of these lines. So all the nodes, all the elements, all the materials. I want to start developing this important skill where you need to be able to glance at the bulk data file, the input file. You need to be able to understand some of the configurations that you see here. So let's go on. Okay, so here on the right, very briefly, this is a model summary. So this is listing all the keywords, all the bulk data entries, all the parameters that are used to define your finite element model, all the Nastran bulk data entries that are used to define your Nastran model. So by the end of the video, you're going to know what the force entry is, what the mat1 entry is. You're going to know what a p-shell entry is, and so on and so on. Okay, and just in case you have any questions, you have any beginner questions, if you have a request for a tutorial, you can contact me at this email address, and then I'll try and get back to you as soon as I can. Okay, so let's go ahead and get started with the tutorial. So everything you see here today, it's going to be done in a web browser. It's going to be done in a web app like you see here on the screen. If you want access to this web app so you can follow along with today's exercise, you can visit theengineeringlab.com. When you come to the home page, here in the top right hand corner, click the blue button, fill out the form, and we'll go ahead and give you access to today's web app. Let's talk about units in Nastran. So Nastran is like a calculator. Or let me re-say that. Nastran is like a calculator. Calculators do not have a notion of units. Calculators don't know what units you're using. The responsibility is on you to manage the units. So before you plug in numbers into the calculator, you've already agreed on a system of units to use for all of your values. During all of your calculations, if you're using units of length, you supply your calculator only the agreed unit of length. For example, if all of my units are in meters, I use only meters when I supply values into the calculator. If I have kilograms for mass, I supply only units of kilograms to the calculator. I never mix it up. If I'm using only meters for all of my calculations, and then I start using millimeters, that's not okay. Your calculator doesn't automatically perform the conversion. You have to convert millimeters to meters, and then you supply your values to the calculator. It's the same thing with Nastran. You agree on a system of units, and then you use those units throughout your entire process of creating the finite element model. So let me go ahead and show you some other examples, some common examples for a system of units. So here you have one system where they use meters, newtons, and Pascal for the length, forcing, elastic modulus, and they use kilograms. So this row is one system of units. If you select this system of units, these are the units used for your entire Nastran model. You don't mix it up with another system. For example, if you were using meters, newtons, Pascal, kilograms, and then you wanted to mix in and use a value with inches, that's not okay. Nastran doesn't have a notion of units. The responsibility is on you to manage your units. So for today's exercise, we're going to be using the following system of units. We're going to be using inches, pound force for the mass, and then pound force for the force. Now, one thing I wanted to do with this exercise is I wanted to introduce this parameter, the weight to mass conversion factor. So for anyone using a density defined as follows, pound force per inch cubed, this is actually a weight density. Normally you specify the density as a mass density. So for example, you would maybe have kilograms per meter cubed. Now, when you use a mass density like the one here on the right, your mass matrix will have units of kilograms. Now, when you use a weight density, your mass matrix will have units of pound force. Now, this introduces a so-called inconsistency, because the mass matrix should always be in units of mass. It should not be in units of weight. So what we're going to do is we're going to introduce this conversion factor, weight to mass, that's going to convert this weight, this unit of weight, to a slench, which is a unit of mass. So that's why we're using the weight to mass conversion factor. We want our mass matrix to have a unit of mass. If you're using kilograms or grams for your density, you don't have to worry about the weight to mass parameter. But here, since we're using pound force per inch cube for the density, we have to use the weight to mass conversion factor. Okay, so let's go ahead and do the following. Let's actually start by defining the weight to mass parameter. So just in case I haven't mentioned it, everything I'm going over today is covered in a PDF with step-by-step instructions. So if you prefer a PDF, that's available at theengineeringlab.com. Okay, so let's suppose you came here to the home page, you fill out the form, and now you have access to the web app. Here on the far right, you would click on this web app pre-post. And let's start off by configuring that weight to mass parameter. So at the bottom left, you would click on pre, and then it opens this new panel, if you will. Here in the navigation bar, look for this link, parameters. Click on parameters, search for weight to mass or WT mass. Here is where you supply that weight to mass conversion factor. And let me make sure I'm using the correct value. So you're done. If you ever want more descriptions on all of these parameters, you can click on one of these buttons, or rather this button, display descriptions. This will give you descriptions of each parameter that's available in Nastran. One other parameter we have to define is the coupled mass parameter. So this basically controls how the mass matrix is constructed. For this exercise, they happen to be using a value of 1 for this coupled mass option. So here I'm also using a value of 1. Here, if you ever want to see the parameters that are in use, you can click on display active. And now it displays all the parameters in use. So let me turn that off. So now we see all the parameters. And when I click on display active, it shows me the parameters that are actually active. Here in the top right hand corner, if you use these buttons, this will actually show you a preview of what's being written to the Nastran input file. So for example, suppose the coupled mass option was 999. You notice that the parameter is updated here on the right. Now, let me download the bulk data file and let me show you what that looks like right now. So we'll go ahead and open the bulk data file. And let me move this to the left here. So this is what our current bulk data file looks like. And you'll notice that it's almost empty because we're starting. We're at the very beginning of the Nastran model. Here are the two parameters that have been created. Now let's go ahead and modify and restore the value for the coupled mass option. So we'll switch that back to 1. We'll go to download and click download. And then we'll inspect this new bulk data file here. And you notice that this field is now 1. You notice that before it said 999, but we adjusted it, we re-downloaded the Nastran model, and now the value is 1. Okay, so we're done with units. We've agreed on a system of units to use during this entire setup process. All of our units of length will be in inches. Our density will be in pound force per inch cubed. We are going to use the weight to mass conversion factor to make sure that our mass matrix is in units of mass. In this case, the unit of mass is slench. Our pound force, or sorry, our units for the force would be pound force. And then what if you're supplying a Young's modulus? Well, that would be F per L squared. In this case, it would be pound F per inch squared. So this is our unit for the Young's modulus. If we have a stress, this will also be our unit for stress. So we're done with units. Let's go ahead and move over to meshing. So the web app has a very simple mesher. This mesher is meant only for training purposes. If you want to create a more complicated mesh, we recommend that you use a separate mesher program. The reason is because web browsers today don't have the performance to create complex meshes. So you still have to download a separate mesher and use the mesher to construct your meshes. Here, let's go ahead and create our plate. And let me go ahead and switch the element type to 2D. Let's go ahead and switch this to a width of 5 inches and a height of 2 inches. And then we'll go ahead and give this a element size of 0.7 inches, and we'll click on mesh. So this is a preview of the mesh. We know this because the color is gray. Remember to click on save. And now the mesh has been stored in the web app. And that's it for meshing. So like I said before, if you want to create a simple mesh, if you want to create some beam elements, this mesher can be used for that. But if you want a very complex and sophisticated mesh, you would use a separate program to mesh, and then you would import it to the web app. Let me actually show, or maybe I'll show you how to do this later on, or rather later on in the video. Okay, we're moving over to a normal mode analysis. So let me walk you through the process for that. So this is what we want to do. For a normal modes analysis, you need two things. You need to define a stiffness matrix, and you need to define a mass matrix. Now, whenever you create a node, so here this black dot represents a node, each node has 6 degrees of freedom. You have 3 degrees of freedom for translation, and then you have 3 additional degrees of freedom for rotations. So you would have something like that. Now, there is a problem when you defined a node. When you introduce 6 degrees of freedom, there is a problem. So here, let's go ahead and write out a stiffness matrix here in the bottom. Whenever you create a new node, the stiffness values are all 0. Now this is a problem for us because in order to solve this expression f equals kx, the stiffness matrix cannot be 0. We have to have non-zero values in the stiffness matrix. So what we're going to define is the following. We're going to define some elements. So we have something like this. We're going to define a thickness. And then we're going to define some material properties like a Young's modulus and a Poisson's ratio, and then a density. We combine this all together, and then our elements are able to generate stiffness values for the stiffness matrix. So after we do all of this, our stiffness matrix will have non-zero values inside. So something like this here in the bottom right. So now let's make sure we have the thickness defined. Let's make sure that the Young's modulus, the Poisson ratio, and the density are defined. So let me look at my notes here on the right. Let's go ahead and shift over here. Let's click on the pre-web app here in the bottom left. Let's go to the bulk data section and go to entries. And let's close the BDF output here on the right. So here on the left is a summary of what exists in the model so far. We have some elements, some nodes, a mat1 and a p shell. And then just in case you want more information regarding these entries, you can click on open entry, you can click on active, and then this will show you the bulk data entries that are in your bulk data file. You can click on display title. This will show you a small preview of what the entry does. You can click on display description, and this will give you even more information about what that entry does. So here for mat1, it says in the title column that this is an isotropic material definition. You can click on any one of these rows, and then it'll switch to that table and that entry. Alternatively, here in the entry section on the left hand side, you can click any row here on the table on the left, and then it will load that entry. So if I click on the C quad 4 row, this loads the element entries. If I click on mat1, this loads the materials I've defined. Here you notice that the Young's modulus, the Poisson ratio, and the density are empty. That's not okay. Our stiffness matrix is going to have 0 values. So let's go ahead and fix that. Let's give this a Young's modulus of 3E7 psi. Our Poisson ratio is 0.3, and our density is 0.282 pound force per inch cubed. Now let's make sure our thickness is okay. We'll switch over to P shell. So the P shell entry is going to help define the stiffness of the 2D elements. Here, all you need to do in this step is modify the thickness. So here, we're going to make sure that the thickness is 0.1 inches. When you do this, back here in the view, if you will, we actually get a preview of what the thickness looks like. Whenever you're dealing with these C quad 4 elements with the P shell entry, notice that we have our elements here, and then we have a thickness like you see here. There's going to be a top side of the thickness and then a bottom side, there's going to be a bottom side and a top side of the thickness. When you look at the stresses are going to be reported either for the bottom or the top side of the element, so just keep that in mind. Okay, so we're done configuring the material and our thickness. So now we expect the stiffness and the mass matrix to have non-zero values. Okay, now let's move on and continue the process of configuring the normal modes analysis. So here on the left, I'm going to look for this entry, EIGRL. Click on the row, EIGRL. Click on create. This is where you specify some settings for the eigenvalue extraction. Here I'm going to say extract any natural frequency between 10 and 2000 Hertz. Next, we want to define a support for the model. So we'll look for SPC1, where the SPC stands for a single point constraint. Click on the row SPC1, click on create entry, scroll down a little, select all 6 degrees of freedom. Let's go ahead and pick the nodes on this edge. So when you look at the picking sphere here, what I've done is I've clicked on the add button here, the plus button, and now I can click and hold and move the picking sphere to make selections. If you click the subtract or the minus button, this will deselect the nodes. One thing you'll notice a moment ago, the picking sphere selected a lot of nodes. You can adjust the size of the picking sphere, so I'll make that 0.1 inches for the radius, and then I'll go ahead and drag and select these nodes on the edge, and then I'm done. We'll go back here, and you'll notice a few things. You'll notice that the list of node IDs has been updated, and the corresponding bulk data entry has been updated for you. So for example, look at field 3, which specifies which degrees of freedom have been constrained. If I select component 3 here on the bottom left, back here on the right hand side, field 3 has been updated to component 3. If I select only components 1, 2, and 3, field 3 here on the right is now 1, 2, 3. So just keep that in mind. This PDF output is a great way to confirm that your changes to your model are being carried over to the bulk data file. A lot of the time, you don't know what's happening in this input file, so you're almost configuring your Nastran model blind. Here, the goal with this PDF output window is you confirm, you know exactly what's going to be written to this bulk data file. Let's go ahead and close this, and let me briefly describe what I just did here. What this is doing is the following. Suppose we have a node. Here, suppose I am supporting components 1, 2, and 3. So this is component 1, 2, and 3. Here, what I'm saying is that the deflection, the displacement of this degree of freedom is 0. The displacement of this degree of freedom is also 0. For this third degree of freedom, this is also 0. Now, when I add components 4, 5, and 6, this also constrains the rotations. So here, the rotation is 0 for component 1. For component 2, it's the same thing. I shouldn't say component 1. That's component 4. This is component 5, and so on and so on. So if we close the pre-web app, we actually show you arrows that represent the degrees of freedom that are constrained. Here, if I only constrain the first component, I get these single arrows that represent a delta equals 0 at each of these nodes in this direction. What does a rotation constraint look like? That will actually give you a double arrowhead. So the rotation at these degrees of freedom are 0. And what happens when I display or when I constrain 3 degrees of freedom? So this tells me that translation in all 3 directions are constrained, and then let's go ahead and make sure all 6 degrees of freedom are constrained. So that's what I did. Delta and thetas are 0 for these degrees of freedom. Okay, now, even though we define a support, even though we define some settings for the eigenvalue extraction, Nastran is not using them yet. You have to tell Nastran to use them. So then this is where we go and navigate to the case control section. And before I go ahead and do that, let me make sure we're on schedule. In this other window, I have the agenda listed, so I'm making sure we're going through the correct steps. Navigate over to the case control command section. Click on commands. Here, we're going to look for this command called method. Mark the checkbox for the above subcase level, and let's actually do this. Let's open the PDF output window. When you mark the checkbox for method, this turns on the method command in the bulk data file. Next, we'll go ahead and switch over to configure, and we'll set this option right of the equal sign. We'll set it equal to the eigenvalue entry that we configured a moment ago. So remember, the eigenvalue entry, we configured it so it extracts natural frequencies between 10 and 2000 hertz. Here, what we're saying is, Nastran, use this entry for the normal modes analysis. I'm telling Nastran extract natural frequencies between 20,000 and 10 hertz and 2000 hertz. Next, let's go ahead and output some eigenvectors. So there are 2 ways you can do this. Here, let me just go over one way. Here, you will use the displacement command. So let's go ahead and mark the checkbox for displacement. And here, we're now telling Nastran, hey, output the displacements from the normal modes analysis. Technically, mode shapes are not displacements. Mode shapes are eigenvectors. So the terminology gets a little mixed up here. After you do this, one thing to keep in mind is the following. Nastran will write out all of your eigenvectors to the F06 file. That's a text file. For a larger model, it's very easy that the F06 file is now 1 gigabyte, 5 gigabytes, 10 gigabytes with text data for all the eigenvectors. There's a way you can disable that. If you switch over to configure, there's a special button here above the table called reduce size of F06. When you click that, it will add some additional commands and the plot describer. So the plot describer is going to suppress the output of those eigenvectors to the F06 file. It's going to reduce the size of the F06 file. Okay, now we're almost done with configuring the normal modes analysis, or actually, let me do this. Let me just run it like this. Let's go ahead and run this. And let's go ahead and get ready for our next step. So here are natural frequencies when there are no supports. So I think here I should describe a few different scenarios. So in this first analysis, I did not assign the supports. I did create the supports, but I did not assign them to a load case. So this is what happens in the results. So let's go ahead and show you what that looks like. And one thing I forgot to do, I forgot to click on add HDF5 out. So what add HDF5 out does, it inserts a new bulk data entry that tells Nastran store the results in an H5 file. So here, let's go ahead and adjust the scale factor. I forget what scale factor I'm supposed to use. So let me look at my notes. Or let me actually fit model and see if I can figure it out. Okay, this is a very large mode shape, and let me reduce this a little more. So here I'm using a scale factor of 0.01 here on the right hand side. If you want to get an idea of what the mode shape looks like, you can toggle this button, click on display shape plot, click on it multiple times to toggle the mode shape on and off. Right now what we're looking at is mode shape 1, and here let me do this. Let me adjust the eigenvalue extraction entry. So we do this. We'll go ahead and disable this for now. We'll say extract the first 15 natural frequencies. So we don't care what value they are, just extract the first 15. So we'll rerun this. So right now what I want to show you are 3 different scenarios for the natural frequencies. That's why I'm going through this. So this is the first natural frequency. So you can see what the shape looks like. We'll go to the next mode shape. And one quick comment about the word displacements. I see a lot of students mix up the words. Here, right now, what we're looking at are mode shapes / eigenvectors. These are not displacements. When you load your model, when you perform a statics analysis, then you get displacements. So keep this in mind. So right now we're doing a normal modes analysis. we're performing a normal modes analysis. So what we're looking at right now are mode shapes. These are not displacements. If we perform a statics analysis, then what we see are displacement, they're deformed shapes. Unfortunately, every now and then I catch a student, sometimes I even catch a professional engineer. They will refer to mode shapes as displacements. These are not mode shapes, they're eigenvectors, they're mode shapes. So right now we're looking at mode shape 2, mode shape 3, and mode shape 4, and so on and so on. One thing you'll notice about the mode shape is that it looks like it's not honoring the support. It's like the support was never there. And that's true. Even though I created the support, I did not assign the support to a load case. So the mode shape is telling us that there's no support on this edge of the model. Let's go ahead and look at the natural frequencies. So if you go to the result file section, click on model.f06 here on the left-hand side, look for this table, real eigenvalues. So let's go ahead and copy this here. So here's our current list of natural frequencies. And let me do one thing. Let me actually describe what this table is. So when I was an undergraduate, this type of table, I've never seen this type of table when I was in school. So the first time I saw this, I realized, well, what is this? What is this? Is this a table? I've never seen this before. So here, what you don't see are boundaries for the table. So let me draw some boundaries so you get some intuition here. So there's an outer boundary, and then you have these invisible lines for the columns. And then you have these invisible lines for the table rows. So you have something like this. I'm not going to draw a line for every row, but I think at this point you get the idea. This is a table with columns. So there's one column here on the far left-hand side. This is the mode number. This other column has the eigenvalue for the mode. And then here on the right-hand side is a column for the natural frequency in hertz. If we look at the natural frequencies, you notice that the natural frequencies are 0 for the first 6 mode shapes. So right now, some of you might be asking, hey, this is not 0. It's actually 1 times 10 to negative 4. This is small enough where it's effectively 0 for the natural frequency. If you ever see a value that's very small, like 1 times 10 to negative 12 or 1 times 10 to negative 8, this value is effectively 0. So even if the value is negative 1 times 10 to negative 8, the value is effectively 0. So keep that in mind when you look at very, very small numbers. Here, since we have no supports, the first 6 natural frequencies are 0. These are often known as rigid body modes. So this is going to be very important later on. So I'll get back to this in a moment. Now let's do this. Let's include the support now. So we'll go to case control commands. We'll go to loads and BCs. We'll click on the SPC row. And now we'll go ahead and assign the SPC. Here in this case, I'm adding it to the above subcase level, so I mark the checkbox. Let's go ahead and rerun this. And let me adjust this title here real quick. So what I've done now, I've included the support in the analysis. I've assigned it to a subcase. In this case, the above subcase level. So this support prevents translation along all 3 directions, the X, Y, and Z directions. And the supports prevent rotation about all 3 axes, the X, Y, and Z. So this plate is in equilibrium. Here, let me briefly shift through the mode shapes. So this is mode shape 1. Let's go and turn on let's click on display shape plot. This is mode shape 1, mode shape 2. And you'll notice one thing about these mode shapes. It appears that the support is now being considered in the normal modes analysis. You notice that the eigenvector values at these nodes, they're 0. That's why there's no, well, it looks like motion, if you will. But here, there is a non-zero part of the eigenvector, so that's why you see here, it looks like an animation, if you will. So there's animation here. There's no animation here. There's no animation here because the eigenvector is 0. The supports have 0 displacement, 0 rotations here. Here it's free, so you have some animation here. Okay, now let's do this. Let's disable some of the support. So we'll go to SPC1. We will disable the support for the 1 and 2 degrees of freedom. And then we'll go ahead and rerun this. So this plate is now allowed to translate along the X, and it's allowed to translate along the Y. And then one thing I forgot to do, let's look at the natural frequencies real quick. So we'll go ahead and copy this new table here. And if we look at this new table, you notice that the natural frequencies for the first 6 modes, they're now non-zero. We get 133 hertz, 689, 842, and so on and so on. So before, we had 0 hertz natural frequencies. So this indicated we had rigid body modes. This indicates not enough supports, no equilibrium. Here we have non-zero natural frequencies, and they happen to be 133 hertz, 689 hertz, 842 hertz, and so on and so on. Okay, so this was the prior analysis. Right now, what we just did, we removed some of the constraints. So now let me rerun this with this updated support. So remember, this version has no supports in the X, no support in the Y. So we'll go ahead and run this with Nastran, and then in a moment we'll look at the new mode shapes. So this is what mode shape 1 looks like. And you notice one difference now. If we look at the animation of the mode shape, you can tell that the mode shape is telling us that it's free to have motion along the x-axis. Let's look at the second mode. For the second mode, it looks like motion along the y-axis is allowed. Let's look at the third mode shape. I believe the third mode shape is going to be like a combination of both the freedom of the x and the y axes. So let me do this. Let me go ahead and copy the new table of natural frequencies, and then we'll go ahead and compare what's going on. So we'll go ahead and paste that here, and then we'll see this. If you look at modes 1 and 2, let me copy them here. You'll notice that they're very small. These are effectively 0 hertz. This indicates we have a rigid body mode. So for each unsupported direction, you get this rigid body mode with 0 hertz. Here, since we have no support along, or rather, since the model is allowed to translate along the X and the Y, we get 2 rigid body modes. So in this latest case, we have a partial equilibrium, if you will. You notice that we're constraining the model in the z direction. So we know the z direction is properly constrained because the mode shape doesn't indicate this. But for the x and the y direction, you notice that there's a problem. The mode shape is actually detached, if you will, from the support according to this. Okay, so now let's go ahead and correct this. Let's go ahead and revert some of the settings. So we'll revert the supports. So we'll constrain all 6 degrees of freedom. And then for the eigenvalue extraction entry, we'll go ahead and revert this to extract natural frequencies between 10 and 2000 hertz. And then there we go. So let's go ahead and rerun this. And we should get something like this table here. Now, what I've done is I'm only interested in natural frequencies between 10 and 2000 hertz. So what you'll see in a moment, only the first 3 natural frequencies will be extracted, because you'll notice that at mode 4 and after, the natural frequency is greater than 2000. So these higher modes, they're effectively not extracted. So let's go ahead and look at our mode shapes, make sure that they're correct. You notice here in this table, we only have 3 modes available. Also, one other thing I forgot to mention, if you look at this section, the domain row, if you will, we get told the mode number. This is mode 3. And then in this row, it tells us what the natural frequency is. The natural frequency is 842 hertz for this mode shape. Let me go ahead and copy the table that has our new natural frequencies. Natural frequencies only between 10 and 2000 hertz. So this is what the table looks like. And you'll notice we only get 3 modes, 3 natural frequencies, because these natural frequencies are between 10 and 2000 hertz. Now, let me go ahead and document these natural frequencies, because later on in this exercise, we'll get back to these natural frequencies. So 842.037. Okay, something like that. All right, then. So I believe we're almost done with this part of the exercise. So whenever you want to save your work, or whenever you're done, you want a copy of the bulk data file. So let's go ahead and delete the old bulk data files. Let's go to download and click on download PDF. When you do this, you get a new bulk data file. So let me close some of this. Let's go ahead and open our new bulk data file. This is what the new bulk data file looks like. You didn't know this, or you didn't see this, but in the background, we were actively creating these bulk data entries. We created the SPC1 that defines the support. The P shell defines the thickness. The MAT1 defines the isotropic material. The HDA5 entry triggers the output of the H5 file that contains the results. The eigenvalue entry, this controls what natural frequencies or mode shapes you extract. We configure the head. So this is what's actively telling Nastran what to do. We told it perform a SOL 103 or a normal modes analysis. Use this support. Output the eigenvectors with the displacement command. So that's the first analysis. Now, with this bulk data file, this for now is all you need. If you wanted to share this with a colleague, a student, a professor, if you ever want to transfer the Nastran model, this input file is all you need. You send this to them, and then they would understand what's going on with the bulk data file. Let me actually show you how to do that. We'll go ahead and open a new pre-post web app. and we'll go ahead and import that bulk data file just to show you what happens. So let's suppose we sent this to a friend and they're looking at the model. So what we saw, they now see. So everything that we defined, everything that was stored in that bulk data file is now on their side. It's in their text file, in that input file. Okay, so I think we're done for the normal analysis part. This part, or rather, a normal modes analysis is very simple to set up. But here I took steps to show you a few different combinations. What happens when the plate is fully constrained? What happens when there are no supports? What happens when the model is partially constrained? All of these different scenarios may or may not have these 0 hertz natural frequencies. They may or may not have rigid body modes. Now, this is going to be very important in the statics analysis, and you'll see this in a few moments. So now we're switching over to a linear statics analysis. So let's go ahead and start off with that. So back in the web app, we'll go to solution sequence here in the navigation bar. We'll go ahead and select SOL 101. So this is telling Nastran perform a statics analysis. Next, after this, we'll go to bulk data entries and we'll look for the force entry. So we'll click on the row that says force. We'll click on create entry here on the right, and then we'll select one of the corner nodes. And then we'll define some values for the force. So we'll define a magnitude for the force. So we'll use a value of 1 pound force. And then you specify the direction of the force. So N1, N2, N3, in this case, it means the X, Y, and Z direction. So here, I only want the force to go in the Z direction. So for N3, we set the value equal to 1. When you close this, you see an arrow. This arrow represents that force that we just created. Here on the left-hand side, if you click on LBC's display panel, click on labels. This will show you some information about that force. This is force ID1. It has a value of 1. Here, you can click on hide all. This will hide all the loads and boundary conditions. Notice the checkboxes have been disabled. You can mark the checkboxes individually to display them. So let's go ahead and just display the support for now. After this, we then define that pressure distribution. So for this, we'll go ahead and look for P load 2, and we'll click on create entry. We'll give this a value of 0.1 psi, or pound force per inch squared. And then for the element IDs, there are a few ways to select elements. Here in the filter box, select 2D elements, click add, and now you can drag and select elements. You can increase the size of the picking sphere, and now you can select even more elements. Alternatively, you can do the following. Sometimes picking a lot of elements is tedious. You can switch over to 2D properties. So we'll select 2D property, select one of the elements, and then the entire property is highlighted. Then switch over to 2D element. All the elements associated with that P shell property are now selected. So that in some cases is a time saver. I wanted to point it out for you. So you notice that now we have the element IDs have been stored in this field, the element ID field. If we open the BDF output, you notice that the entry is updated for you. And remember, anytime you modify a value here on the left, so 1, 2, 3, 4, 5, 6 for the pressure, the bulk data entry on the right is immediately updated for you. Remember, the goal of the tutorial is to show you how to build these bulk data entries. This is going to be very critical if you want to be successful with Nastran. So here, let me go and revert the pressure to 0.1. And now we're done. We've define the two loads. And I believe that's it for statics analysis. Let me look at my notes here on the right. I think that's it. Let's go ahead and do this. Let's go ahead and hide the pressure distribution. So this is a bunch of arrows that represent that pressure distribution. You can click on display labels once or twice. Depending on the number of times you click on display panels, you will either see a limited amount of information, or you will see more information that tells you some information about the values of the loads. So let's go ahead and do this. Let's only show the support for now. Okay, now, just because we've created the loads does not mean Nastran will use them. We have to tell Nastran to use them. So to do this, we're going to assign the loads to load cases. So we'll go to case control commands. We'll go to subcases. Let's go ahead and add a new subcase. Here, click on renumber subcase IDs. So for example, let's suppose the first subcase was subcase 1000. This is going to cause an error because the subcase numbers should always be in ascending order. So you can click on renumber subcase IDs, and then this will fix the numbering for you. So now instead of subcase 1000 and then subcase 2, you have subcase 1 and then subcase 2. And then here on the right, you now have subcase 1 and subcase 2. Once you have these two subcases or load cases, you'll go to loads and BCs, go to navigate, go to load. We'll go ahead and assign the force to subcase 1, and the pressure distribution gets assigned to subcase 2. And we're done. Let's go to download and upload PDF and run. And then after this is done, give it a moment. I'll go ahead and load the deformations. So let me repeat this again, that when we perform a normal modes analysis, the shape that we saw, it was a mode shape. It was an eigenvector that we saw. It was not displacements. Now that we're performing a statics analysis, what we see are displacements, deflections, deformations, deformed shape. So these are displacements. So one thing you can do here, we're looking at load case 1. Let's increase the scale factor. A lot of the time, the deformations are so small you don't realize that the structure has deformed. So a lot of the time, you need to increase the displacements. You need to scale up the displacements so they're noticeable. Here, let me go ahead and increase. Let me use the scale factor of 100 actually. So this is what the deformed shape looks like. Let's go ahead and switch over to the second subcase, the second load case where we have the pressure distribution. Here the deformation is a lot less than before, but it's there. One other thing you could do here, you can select one of the maximum or the minimum labels. This tells you which node ID or grid ID has the minimum or the maximum value. You'll notice here in the data set, there's no option for the stress. That's because we have not told Nastran to output stress. Let's go ahead and output stress. We'll go to case control commands, and we'll go ahead and look, and here, click on select. So the select section, in the select section, this will show you all of the commands that are available in Nastran. Here we know that the command that we want is stress. So we'll turn on stress by marking the checkbox. Here on the right, you'll notice that stress equals all is on. We'll go ahead and click on reduce size of F06. And now you'll notice that stress is using the plot describer. So the plot describer is telling Nastran, hey, yes, I want the stresses, but use the plot describer. Do not output the data to the F06 file. I don't want a big, massive F06 file. When you do this and run Nastran again, you have a new data set, stresses. Let's go and select stresses and look at the first load case. When you do this, you have to specify what value you want to look at. So right now we'll look at von Mises stress for the bottom side of the element. So remember, these 2D elements have two sides, if you will. There is a bottom and a top side. When you look at the stresses, each component of stress, if you will have this annotation. It will have Z1 or Z2. Z1, what the Z1 and Z2 terms are, Z1 is the distance from the midplane, it's the distance from the elements to the bottom side of the thickness. And then Z2 is the distance from the elements to the top side of the element. So that's what Z1 and Z2 are. And what's done here in the web app, they're labeled with bottom and top. So right now what we're looking at the von Mises stress at Z1, which is the bottom of the element. And then if I wanted to, I could switch over to Z2, which would be the von Mises stress at the top side of the element. Now, one thing you'll notice about the stresses, each element has one stress value. The stresses at the moment are being reported at the center of the element. There are no stresses at the nodes of the element. So how do you output the stresses at the corners, at the nodes of the elements? So for this, we have to adjust the stress command. Here, what we're going to do, we're going to press and hold the control key. When we do that, we can select multiple describers here in this list. Let me scroll down and look for this option, the bilin option. So we'll press and hold the control key. We'll select bilin. So I should have bilin and plot selected here. So what the bilin option is doing, let me go ahead and actually show you something I haven't mentioned before. One very important document you'll need when you're working with Nastran is the Nastran Quick Reference Guide. This is basically a dictionary for all the entries, all the parameters, all the commands you find in the bulk data file. So what I'm going to do now, I'm going to look for the stress command. I'm going to look for stress, case. I'm going to scroll down to this table. You notice that there is a column for describer and the meaning. I'm looking for the bilin describer. And here I found it in this row. Let's look at what the meaning is. So when you use bilin or corner, this requests C-quad 4 element stresses at the center and grid points using bilinear extrapolation. So this option, the bilin option, alternatively you could use the corner option too. This will tell Nastran, hey, output the stresses, I'll put them for the center and the corners of the nodes. So let's go ahead and do that right now. And we'll give us a moment to load the results, and we'll go ahead and take a look at the stresses in a moment. So let's go ahead and select stresses here on the top right. We'll look at the first load case, and then we'll go ahead and select von Mises stress for the bottom maybe. Next, we have a new option here in this row, location. So this option was absent before, but now it's present. Right now it's set to center. We're looking at the results. We're looking at the stresses at the center of the element. Now I'm going to switch over to corner. Now I'm looking at stresses at the corners. So you notice that there are gradients from corner to corner of the elements. Okay, one other thing. You have these other options like X1, Y1, a shear XY, 1. So these are going to be the normal stresses. So let me draw it out for you. Let me see if I have a page here. So if this is our element, we're going to have a stress reported in this direction, and then a stress reported in this direction. So let's go ahead and look at this. So this is going to be labeled X1. So this is component X1, and then I believe this component was Y1. Now you might be asking, okay, how do I know what the x and the y direction are for the elements. So the way you do that, you go to orientations. Let's rotate this model a little. Or actually, let me go here. Click on material coordinate system. So then this is going to display the x and the y direction for each element. So you notice we actually use stick figures to help communicate what's going on here. So the stressors are being observed at the center by the stick figure. So let me do this. Let me take a screenshot of this. Let's go and take a screenshot of this. Right, these are the material coordinate systems. And let's go ahead and paste that in a separate page and maybe enlarge this a little. So now for each element, there is a sigma x and a sigma y. And then you have a shear stress on the xy. So remember that. So sigma x, sigma y, and so on and so on. So that's, if we go back to the post panel, that's what x1 and y1 are. And then we have x2 and y2 for the top side of the element. Remember, since this is an element with thickness, we get values for the bottom and the top. Okay, so I think we're done with stresses. And now let's go ahead and move on to another topic that I wanted to cover. Let me see if I have it here in the web or in the PowerPoint. Okay, so one last thing. So now that we're done, we'll go ahead and download this. We'll download the PDF file. And let's go ahead and rename the bulk data file. So this first bulk data file, this was a normal modes analysis. The second file was a statics analysis. So remember, the bulk data file contains the entire description for the Nastran model. Notice that we have our two load cases, the output command for stress, definitions for the pressure distribution, and the force. So now we can send this to a friend, a colleague, the professor. And this is all they would need to look at the Nastran model. Okay, right. So let's talk about one very common problem that new Nastran beginners are going to have. This is the user fatal message 9050, 10030, 10031. So let's go ahead and first replicate this error. So if you remember when we perform a normal modes analysis, during that exercise, I purposely left out some support. So for now, let me remove the constraint for the x and y directions. And let me rerun this. And let me actually turn off the loads. So this model is not supported in the x and the y directions. It's free to translate in these directions. The model is not in equilibrium. The fact that the model is not in equilibrium triggers this error. So let's go ahead and do this. Let's go to pre. So when there's an error, and here you notice that it still has some results, and I'll explain what the results are in a moment. So what's going on here is the following. Let's suppose that, or let's recall that we're trying to solve this equation, F equals kx. So x represents the unknown displacements. When you have something like this, suppose we have a beam on two rollers like this, and then we have a force in the middle going in the horizontal direction. You notice that this model is not in equilibrium. It's allowed to have translation in the horizontal direction, if you will. So now what happens here? What happens in this expression? You have this scenario where you have either no solution or you have multiple solutions. So here in this case, I suspect there might be multiple solutions in this case. Of course, I need to confirm it by looking at the stiffness matrix and trying to solve this. But here, I suspect any one of these solutions will be correct. You can have translation here. This would be one of the solutions. You can have maybe translation here. I know it's not intuitive, but I've seen it. You can actually force the finite element solver to try and find a solution, even though the solver tells you, hey, there's a problem here. So here, I suspect what's going on here, there are multiple solutions that exist. Multiple solutions. So user fatal message, or UFM 9050 is triggered. Now in newer versions of Nastran, the error is 10,030. So for this expression here, these are the scenarios you're going to have. There is no solution. So this might happen if you forgot to specify Young's modulus. What happens when you forget to specify Young's modulus, your stiffness matrix might have all zeros. So in that case, there's no solution. Actually yield a trivial solution. Here, let's go ahead and look at a different case. Multiple solutions. So multiple solutions. This is typically when you don't have equilibrium. There's no equilibrium, I'll say. You get the point. And then unique solutions. So ultimately, that's what we want. We want a unique solution. So this is only possible when you have enough support to have equilibrium. So how do you make sure that you have equilibrium? You open up your statics book and you look at what the equations are for equilibrium are. So you have to make sure that the sum of the forces in the x, y, and z and the sum of the moments about the x, y, and z, that they're all zero. For this case, you notice that the sum of the forces in the horizontal direction, they're not equal to zero. There's no support, there's no reaction, so there's no equilibrium. We get this error. So if we look at this message here on the right, we get shown the F06 file automatically, and now we see the error messages. So let me copy these errors to a text file, and let's go and read along the error message, and let's go and read it. Static analysis terminated due to excessive pivot ratios in matrix KAL. So basically, this is a technical way of saying that there is either no solution or there are multiple solutions. So there's a problem. There's a problem in the stiffness matrix. That's what the Nastran is telling us. So what Nastran does in newer versions, it actually tries to perform the analysis, but it defaults to a normal modes analysis. Remember, we have statics analysis selected, but since there was an issue during the solution, it's defaulted to outputting eigenvectors. It outputted mode shapes. So this is kind of convenient for us because we can actually flip through the mode shapes, and we can use this to hopefully identify what the problem is. So let's go ahead and switch the scale factor to 0.1. Let's go ahead and increase that to maybe 1. So here we'll turn on the mode shape on and off. Okay, so this is clear evidence that we have no support in the x direction. Let's go ahead and switch over to mode shape 2. And we'll turn it off and on. So even more evidence that there's no support in the y direction. So again, this is done automatically in newer versions of Nastran. Let's go ahead and see if there's a natural frequency table. Let's see here. Right, so before before we saw these tables with the natural frequencies, unfortunately, those are not available here. If they were visible, we would have something like this. So let me go and see. Right, so we would have something like this. Actually, let's do that. So let's suppose that these mode shapes are not automatically here. Let's switch to normal modes analysis. So Sol 103, and let's rerun this. So I want everyone to know how to perform a normal modes analysis. A normal modes analysis is a very effective strategy to identifying parts of your structure that are not properly supported. So here we'll look at mode shape 1. And then one thing I have to do, always remember, here there's a problem with this eigenvalue entry. Let me actually create a second eigenvalue entry. Let me extract 15 modes. This first eigenvalue entry, it's configured to output natural frequencies between 10 and 2000 hertz. If there is a natural frequency with 0 hertz or near 0 hertz, it's not going to be extracted. So I'm creating a second eigenvalue entry. And then I'm going to tell Nastran, hey, use this other eigenvalue entry. Use these different settings. Use the second entry that says extract the first 15 natural frequencies. So let's go ahead and look at our new mode shapes. So we'll go and wait for the post app to open here. Okay, so now we have more mode shapes. Let's go ahead and turn this off and on. Okay, there's a lot of motion there. It's going to decrease the scale factor to 0.1 maybe. And let's zoom out. So this is what the first mode shape looks like. And then this is what the second mode shape looks like. So if we look at the row natural frequency, you can see that the natural frequency is 0.0011 hertz. So it's very small. It's very close to 0. Let's look at mode shape 3. So for mode shape 3, I believe we get 54 hertz. So this is a non-zero natural frequency. So we're only focused on the first and second mode because they have 0 hertz natural frequency. This is indicating a rigid body mode. Basically, the model is allowed to translate, but there's no deformation that occurs. You only have translation, it's not properly supported, so there's no deformation. So again, a normal modes analysis is a very useful strategy for identifying where your model is not properly supported. If you know how to configure a normal modes analysis, you will be a very good Nastran user, if you will. So now let me do this. Let me revert some of the settings. Let me switch back to using the first eigenvalue entry. Let me delete this temporary eigenvalue entry. Okay, so that was how you fix a user fatal message 9050. I believe we implemented the fix, or actually let's make the fix. So we'll select all 6 degrees of freedom. We're properly supporting the model. And then we'll rerun this. We'll make sure that this error no longer happens. So this is UFM 9050 or 10,030. Okay, so it's complete. And that's good. That's indicating that we have no error. And let's go ahead and look at the results. Do we get... Oh, and I forgot to switch this back to statics analysis. So let's go ahead and rerun this. Let's make sure we get displacements and stresses from the statics analysis. And then here in a moment, we'll see that there are stresses and there are displacements. And let me make a side comment real quick. Let's download the F06 file. One comment about this table. Suppose you want a copy of all the result files. You can click on download one by one. So here in the download column, click download, download, download. Here, I'll click download for the F06 file. Or you can mark the checkboxes one at a time, or you can mark all of them with this one button. And then you click on download selected files. And then all of that data is in a zip file. It's been downloaded in a zip file. Now, one action after every analysis that I recommend, open the F06 file and look for user fatal message. User fatal message. If you ever see that error, stop. Do not look at the results. That's a critical error that has to be resolved. In other rare cases, you would see this other error. System fatal message. So for now, let me just look for fatal message and see if we get any hits. Okay, so if you look at the results here in the bottom left, there are 0 results found for fatal message. Now, what happens if I manually copy this error here? So let's suppose that there was an error. So what we do, we look through the entire file for this message, fatal message. If you ever have fatal message, inspect the error, fix the error, then try to perform your analysis and look at the results. So here, stop here, fix the issue, then try again. Here in this case, there was no error, so we're good. Okay, so there you have it. That's how you trigger the error. That's what the error means. It means that you either have no solution or you have multiple solutions. Either there's something wrong with your stiffness matrix or there's no equilibrium. The goal is a unique solution. So this happens when your stiffness matrix has non-zero values and a unique solution is guaranteed. Okay, what are we doing next? We are now ready to move on to the last part of this exercise. So if all you're doing today is a statics analysis, that's it. You're done. You don't have to keep watching. This next part of the video is for anyone who's performing a type of dynamic analysis called a frequency response analysis. So let's go ahead and get started. Let me move this to the side actually. Let's first go to solution sequence and set this to SOL 111. So this is the modal frequency response analysis option. Let's go ahead and now specify some excitation frequencies. So when you read the documentation, this term is going to have many synonyms, if you will. Sometimes they're called forcing frequencies. Sometimes they're called solution frequencies. So here, I'll mostly use excitation frequencies, but sometimes I might use forcing frequencies or solution frequencies. They all mean the same. Now, this is a big difference between natural frequencies. These are not natural frequencies. So keep that in mind. These are something else. So these are the excitation frequencies. Let me actually show you in this diagram what they might look like. So here, this is what you should expect by the end of this part of the video after the frequency response analysis. Each point is the excitation of frequencies. So we're performing the analysis at 20 hertz, 40 hertz, 60 hertz, 80 hertz, and so on and so on. So we want to first define all these points. So the way we do that is we look for frequency and we click on the frequency 1 entry. So here, for now, let me click on frequency. What you can do here is you can manually list the natural frequencies you want to use. So if you want to use 20 hertz, 30 hertz, 40 hertz, and so on, you could do that here. You get a plot with all the excitation frequencies, if you will. And then here on the right is a preview of what the entry looks like. Listing all the entries, or listing all the solution frequencies one by one, is obviously tedious. So there are other entries available to program your excitation frequencies. You can use the frequency 1, 2, 3, 4, and 5 entry. Here in the exercise, we'll use the frequency 1 entry. We'll click on create. And then for the starting starting solution frequency, we'll say 20 hertz, go in increments of 20, and repeat 49 times. So here in the plot, we get a preview of what the excitation frequencies look like. If we hover over the value, we get a label on the horizontal axes. This is 20 hertz, 40 hertz, 60 hertz, 80, and 100 hertz. This is matching the points on our displacement versus solution frequency plot. Okay, so now that's one of the more easier ways to define your excitation frequencies. There is an alternative way to define your solution frequencies. And for that, we're going to switch over to the frequency 4 entry. So we'll go ahead and click on create entry. Here we'll say, consider only natural frequencies between 20 and 1000 hertz. We'll say that for each natural frequency, have a spread of 0.03, and at most, create 5 evenly spaced solution frequencies. So here, let's go ahead and look at what we have here. Let's suppose we had a natural frequency that was 500 hertz. So for the list of dummy test natural frequencies, we'll specify 500 here. We'll click on this row for F1, this orange line. This vertical line represents 500 hertz. We'll click on this row. This is going to show us a distribution. And then when we click on this row in the legend that has the cross markers, let's go ahead and drag and select so we look at this in a closer view. This is going to show us the solution frequencies based on this natural frequency at 500 hertz. Now you'll notice that this diagram is matching the diagram in the quick reference guide. So if you look at frequency 4, scroll down, we have a diagram for amplitude versus solution frequency, and then here we have the half power bandwidth. So that's the almost the same thing that you see here in the plot. Now suppose we have another natural frequency, 800 hertz. So then this will give us 10 additional solution frequencies. So let's go ahead and take a look at what that might look like. So what you do here is you double click on a row to toggle whether or not all the legend entries are selected or not. So for F2, let's go ahead and select all those. And let's zoom in. So here, as expected, we have 5 evenly spaced intervals, if you will. Let's go ahead and switch the number to 8. So NFM is set to 8. And now if you count, we then have 8 evenly spaced out solution frequencies, like you see here. Okay, let's revert that to 5. And let's make this one comment. Remember that when we perform the normal modes analysis, we had these natural frequencies. We had 133, 689, and 892. So what I'm going to do is, let me go ahead and look at my notes. I'm just going to use these natural frequencies. So these are the same ones, just more in a human readable format. So let's go ahead and copy that. Let's paste that here. So these are going to be the solution frequencies that are created from the mode shapes that were determined during the normal modes analysis. So in total, we have 3 mode shapes, 5 solution frequencies per mode shape. So in total, we have 15 solution frequencies in this list. Now, say we want to combine all of the solution frequencies together. We have the frequency 1 entry with these solution frequencies. We have the frequency 4 entry with these 15 solution frequencies. Suppose we want to combine all of these together. Modify the identification number of the entry so it's equal to the other entries. So if the frequency 1 entry has an ID 1, for the frequency 4 entry, we'll go ahead and change the ID to 1. So now Nastran will see this and will say, okay, I'm going to combine all of these solution frequencies together. All of these excitation frequencies, all of these forcing frequencies are going to be combined together. So let's go ahead and do this. Let's click on plot entries with same ID. And here is a summary of everything that's going to be considered. So if we zoom in, we see 20 hertz, 40 hertz, 60 hertz, 80, 100, 120. And then we have this, 129, 131. So these are the solution frequencies from the first mode shape. So 129, 131. Let's go ahead and look at this plot that we'll create in the future. So we have 20, 40, 60, 80, 100, 120, and let me zoom in because this gets a little complicated. 120, and then we have these 5 excitation frequencies: 129, 131, 133, 135. These are the ones from depending or based on the natural frequencies, and then I believe they will actually coincide. So let me look at here. 133, 689, 184, 842, sorry. So 689 and 842. Okay, perfect. So at natural frequency 133, we have a peak in the response. At 689 hertz, we have a peak at the response. And then at approximately 842, we have another peak also. All right then, so we're done with the excitation frequencies. Let's go ahead and tell Nastran to use these excitation frequencies. So we'll go to case control commands, we'll go to select, we'll look for frequency. We'll turn it on for the above subcase level. And then for configure, we'll go ahead and tell it, hey, use this entry, frequency 1. And notice that the other frequency entry, frequency 4, has ID 1. So Nastran knows, okay, I'm going to combine all the entries that have an ID equal to 1. So now Nastran knows to use all of these excitation frequencies. Okay, what is next? So this is where we switch and we define the dynamic load, I believe. So let's go ahead and let's do this. Before I go ahead and create, or rather, yeah, let's just go ahead and create the dynamic load right now. We'll go ahead and go to this section, bulk data entries. Now, one thing to note about this section, there are 3 sections in this one location. There is a top section, a middle section, and a bottom section. A lot of the time when you're configuring the bulk data entries, they are going to be dependent on one another. So in a lot of other programs, there's a lot of back and forth in the interface trying to track down the entries and configure them. So it sometimes is kind of a mess. Here in the web app, we're doing something a little different. At this moment, it's kind of an experiment. What we're going to do is this. We'll scroll down to the middle section. We'll look for this entry, table D1. We'll click on the row and we'll open that parent. We'll open that entry here. And we'll create an entry here on the right. Here on the top, we'll look for the rload2 entry. And we'll click and select that. And we'll create entry here. So now, this entry is going to depend on a table D1 entry. So instead of me running back and forth, I'm going to display these tables, these entries together like you see here, so I can jump back and forth between them very easily. Okay, so for the table D1 entry, that's going to be used to define this term. So let me go ahead and show you what that term is used for. Table D1. Oh, sorry. I'm looking for Arlo 2. Arlo 2. So this is the dynamic load. So let's actually talk about this dynamic load for a moment. So let's copy that here. So for now, we're going to be focusing on the so-called temporal part of the dynamic load. So temporal. So in this next step, we're going to look at defining this function, if you will, b of f. So this is how we're going to define b of f. We are going to go to that table D1 entry that we created a moment ago. We're going to click on add row 2 times. And then we're going to say at 10 hertz, at an excitation frequency of 10, b of f is equal to 1. And then at 1000 hertz for the solution frequency, b of f is equal to 1. So these are the 2 points, and then Nastran creates an interpolation function. So you get something like this. Let me make this a little bit more complicated. So let me say that at excitation frequency 1000 hertz, the value is 10. Now, when we look at this, we say at B500. Let me make sure that's the value we can select here. At excitation frequency 505. So if you look here at the horizontal axis, this is 505. What is b of f? So at b of 505, what does that value give you? That gives me a value of 5.5. So at B505, that gives me a value of 5.5. And so we'll get back to this in a moment. So once we're done configuring this function b of f, we'll now configure our dynamic load. So for this, let's go ahead and supply a phase term. So we'll say have a phase of negative 45 degrees. And then for b of f, which would be this column, TB, RB, we'll click on this toggle icon, this toggle button. So before you can specify values of like 1. So when you use 1, when you use a constant, this is saying that b of f is a constant of 1. But here we want our function to vary. So for this, we're going to say b of f should point to the table D entry we created a moment ago. So here we selected table D1 ID 1. Here on the right, we get a preview of what the dynamic load is. So this plot is the temporal part of the dynamic load. Now, there are going to be 2 components for this. There's going to be a magnitude and then a phase term. So for now, I'll focus on the magnitude portion of this. So let's go ahead and deselect phase. So let's go ahead and see here, maybe. Oh, right. So one quick comment about the bounds. We know that our solution frequencies, I believe, go from 20 hertz to 1000 hertz. I actually forgot. Let's go ahead and remember what they are. So frequency 1, we're going from 20 hertz to 1000 hertz. Okay. So let's go back to our load 2. So we'll set the bound from 20 to 1000. So this is what the temporal part of the dynamic load looks like. We'll look for 505. Okay, so here, rather than make this a really long story, I'll say this. What you do is you know what the, here I'll give you an example. Suppose that f equals 500. 505 as an example. 500 hertz. You determine what B 505 is. You determine or basically you plug in f is what I'm trying to say. You plug in f here into this expression that gives you the magnitude and phase, and then you get the dynamic load that you see here. Okay, now one thing we have to do now, we have to define the load. So this is the temporal part. This is the load. So let's go ahead and select the load. So for this first load is going to be for the force. So this is the dynamic load, if you will, for the force. Let's repeat this by clicking on create entry. We'll say this is for the pressure distribution. So we'll select P load 2. And then here, what I have in my notes is that BFF is equal to the table. Now, one very convenient thing about these plots is the following. Whenever you modify the interface, the plots are automatically updated for you. So now let's actually make this negative 100. So it's negative 100. This plot is updated. These plots are also updated. From what I have in the PDF, it looks like we're doing a very simple example. So we'll set that equal to 1 here. And then we'll look at this, and the plots are updated. And let's go ahead and look at the bulk data entries. So again, we are actively building out the bulk data file. We confirm that we see the entries. One challenge with a lot of other programs, they have something I'll call object permanence issues. Actually, I don't know how to spell permanence. Let's go and look at that. Okay, I got lucky today. Sometimes you'll click OK, you'll click apply, and then you realize that, hey, my entry was not saved. Work was not saved. So that's kind of an active challenge when you use a lot of programs. Always remember to click OK and apply. Here, the way we make sure that the object exists and stays is by looking at the BDF output. If you see it here, it's guaranteed to be included in the final bulk data file. Okay, let's go ahead and see where I'm at with this. I believe at this point we're moving on to damping. Okay, so this is going to be one way of specifying damping. So let me go ahead and make sure I'm looking for this correctly. Tab DMP1. We'll open that. We'll create entry. We'll add 2 rows. For the type, we'll say use the critical option. And then for the rows, we're going to use this. So for any natural frequency between 0 and 10, use a damping value of 0.03. And now we have to tell Nastran to do this. We have to tell Nastran to use this damping setting, and we have to tell Nastran to use the dynamic loads that we define. So let's go ahead and navigate to case control commands. We'll go to commands and select, and we'll look for S damping. We'll turn on that checkbox. We'll go to configure, and we'll go here and say use the damping table that we created a moment ago. And then as always, let's make sure that this was honored. Let's make sure the work is being saved. If you look on the right, there's a new command, S damping, and it's pointing to 2. That's going to be the identification number of that table, of the damping table that we created a few moments ago. So tab DMP1, ID 2. Okay, now let's work on the dynamic loads. So maybe we'll do this. Let me see. Let me look at my notes. I can't remember if we delete the subcases. It looks like we delete the subcases. Okay, so let's do one thing. Let's make sure that the SPC is assigned. Let's make sure that the boundary condition is assigned. So here we've assigned it to the above subcase level. Let's go to subcases. Let's delete the old subcases. Let's create a new subcase. Let's go ahead and confirm the SPC was assigned. Let's make sure. This is something you might have to do a lot, actually. You might unknowingly remove the assignment for your loads, boundary conditions, or dynamic loads. So inspecting the assignment is something you should do often. We'll go to navigate. This time we're going to deload for dynamic load. So we'll click on this row. And here we'll simply assign the dynamic loads to subcase 1. This is what the final results look like. Okay, now we'll go and run this. Now, if you notice here, we have this plot this command. We're saying output the displacement for all the nodes. Now, we're going from 20 hertz to 1000 hertz. There might be 100 solution frequencies, if you will. So this is going to trigger the output of a lot of data. So your maybe the F06 file or the H5 file will be 1 gigabyte big, 10 gigabytes big. It would be very large. So the question now is, how do you reduce the amount of output? So we'll go ahead and talk about that in a moment. So here, let's go ahead and look at the displacements real quick. We'll look at this for solution frequency at 20 hertz. So we'll mark the first checkbox. Or actually, let me go to 133 hertz. Was it 131? It was 131. So the values are very small. That's why we're getting this. Let me go to ZM. So we want to look at the Z component magnitude term. One thing you'll notice when you look at the results, you'll either get real imaginary values or you'll get magnitude and phase values. So just keep that in mind. So here we're getting displacements for every node, for every force and frequency. So you can see here there are rows and rows and rows of data. This can cause a very large results file. So how do you limit the amount of data? So what we're going to do is create what's called a set command. So we'll search for set, click on the row set, click on create. We are going to select specific IDs for output. So let me hide the pressure distribution. So what I've done here is I've selected these 3 nodes. So we only want data for these 3 nodes. Next, I'll go to the case control command section. I'll go to commands. I'll go to configure. Look for the displacement row. For this option, set it to that set command and rerun it. So we're telling Nastran, hey, output the displacements, but only output the displacements for those 3 nodes. So we'll go ahead and let this run and finish. This will automatically open the color plots. The color plots are going to look different now. Before, we had data for all the nodes. So all the nodes were colored. But now, we only have data for 3 nodes. So only 3 nodes are colored. But this is not what we're interested in. We're not interested in the color plots. What we're interested in are these graphs. So let's go ahead and talk about how to create those graphs. Here, go to run result files. Go to this row, model.h5. Notice one thing. The H5 file is 1 megabyte in size. I believe before it was maybe 5 megabytes or 2 megabytes. So we've reduced it to 1 megabyte. If this was a larger file size, before you might have 10 gigabytes, and then after you might have maybe 100 megabytes. That's a significantly reduced amount of data that you have now. Let's click on View Results HDF5 Explorer. This will open a separate web app. The web app will detect that you only want graphs for 3 nodes, and it will automatically create the plots for you. If you have 100 nodes, the web app will automatically create the plots, the graphs for 100 nodes. Here, let me explain how to differentiate these 3 plots. If you look at plot number 1, the title says ID2. This is for node or grid 2. The second plot is for ID3, node 3. The last plot is for ID16, node 16. So if you ever want to look at the plot, click on the image. This takes you to the actual plot. Now, there are a few things you could do here. Click on View Filters and Plotted Values. You can mark this checkbox, show max peaks, and this will actually put labels at the peaks in the graph. One other thing you could do, you can click on Download CSV. This would download a CSV file. So then you can go ahead and open it in Excel and create the graphs on your own. So here, I believe, let's go ahead and see if we can get this to work here. Let me go ahead and open my other window. Let me open the Excel file. Let me confirm I can do it before I show you. A lot of the time, if you do a tangent, let me look at this real quick. Yep, this is right. I have like a script. I have a tutorial set of steps. Every now and then, if you deviate from the steps, it's very easy to make a mistake and then your tutorial goes all wrong. So that right now I'm deviating. So here I have the CSV file that's been downloaded here. Let's go ahead and open it in Excel. So this is what the CSV file looks like. One row is for the solution frequencies, the excitation frequencies, the forcing frequencies, and then this other row are the actual displacements. So let's go ahead and create an XY plot or a graph. So this is what the graph looks like, and you could do formatting on your own. You could add axis labels, or alternatively, you could use the web app for that. A few other things you could do here. You could use either a linear option for the vertical axes, or you could use a log scale. Also here on the top right hand corner, you can hide and show the different plots, graphs, or you can click on display markers. And this will show you the points. So the points are the actual points that were outputted by Nastran. And then your graphing program will connect the dots with the lines. So here in Excel, let me show you what I mean by this. So in Excel, let's do this. So Nastran just gives you a bunch of points. And then the web app connects the dots for you. Here, let me go ahead and turn on the log scale for the vertical axes. So here we'll turn on the logarithmic scale option. And now you can see that this plot looks very similar to the plot we have here in the web app. Okay, now let me show you another way to get this data. So what you would do is this: go to case control commands, go to select, or go to configure rather. Go and set, let's see, what did I do? Deselect plot for now. So notice here on the right side, it's displacement equals 1. You could also select print, and leaving print in or out means the same thing. A reminder, plot says output the data, but do not output the data to the F06 file. If you remove that, Nastran will then by default output the data to the F06 file, or you can select print and it will also print the data to the F06 file. Let's go ahead and rerun this. Right now, I want to show you another location where the data comes from, because I know some of you might see different tutorials and you'll see different things. So I want to cover the other methods of getting this data for the graph. Okay, so wait a moment, because the post app wants to open. Go back to pre, go to result files, go to F06. So this is what the data looks like now. Let me go and see where we're at. Let's go ahead and copy some of this data. So right now we're using this option, displacement equals, what was it, 1, displacement. So both of these configurations are the same. This is what the output looks like. Now, one thing you'll notice about the output, it's outputting real imaginary terms. So you see it here in the title, real/imaginary. We want magnitude phase values here. So how do we do that? You go back to the displacement command and you select this other describer. You select the phase describer. Let's go ahead and rerun this now. And while that's running, let me go ahead and copy this here so we see what the difference is. So we've added phase, and let's go ahead and see where we're at with running this. Okay, we're complete. We'll go ahead and wait a moment for this to load the post panel. It opens the contour plot by itself. So we wait. We go back to result files to go to F06, and let's go ahead and select the new tables. In the new tables, you'll notice that now it says magnitude phase. Now there's one other tricky thing about the formatting. You notice that here we get this title. These are the displacements for solution frequency 20 Hertz. We get values for node 2, node 3, and node 16. But this is going to make it a little complicated, because in the next table, these are the displacements for excitation frequency 40 Hertz. We have rows for node 2, node 3, node 16. So say I wanted to create a plot for the X direction for node 2. I have to copy and paste. Where am I at? I have to copy and paste each value one by one. So this is a little tedious. So I'll show you an alternative method. You can select this other option called sort to. This is going to change the format of the output table. So let's go ahead and take a look at the new results. And then, like I said before, the post panel wants to open, so we'll go ahead and wait for that to open. And then after that, we'll jump back to this F06 file. Okay, so let's go ahead and scroll to one of these tables. Okay, so let's go ahead and look at this table, point 16, and I'll copy the first few rows. Okay, so this table is for the following. Let me copy the command. So this example is for this. So here we're using the sort to option. So before, we have multiple tables, one for 20 Hertz, one for 40 Hertz, one for 60, 80, 100 Hertz, and so on and so on. When we use sort to, we now get one table for the node. So here we have 20 Hertz, 40 Hertz, 60 Hertz, 80 Hertz, and so on and so on. So now I can select the column for T1 and I can copy the values somewhere else. But this is still not final. There's still some complications here. So let me describe what the complications are. You notice that you get 2 rows for each excitation frequency. What are these 2 rows? So let's go ahead and take this row and let's move it up. Let's combine these rows actually. So let me combine these 2 rows together. So we notice that here we have row 2. So this is going to be T1, T2, T3, and so on and so on. So these first few components, these are the magnitude components. Parts, terms, whatever you want to call them. So these first 6 components are the magnitude component. The next 6 terms, these are the phase components. So the F06 file is actually limited. I forget if it's like 100 characters long or 128. So instead of showing you the data in one row, it actually splits the row into multiple rows. So that's why you see 2 rows per excitation frequency. 1 row is for magnitude, 1 row is for phase. Now, for node, let's go ahead and do this. We are looking at node 2. So let's do this. Let's download the F06 file. Let's open this in the text editor. Let's do one confirmation. The peak happens at a excitation frequency of 133 hertz at 0.2. Let's confirm that in the F06 file. So let's look for these displacement tables. Let's look at excitation frequency 133. So that'll be this row. Let's maybe combine, let me look here. Yeah, let's combine this row. So let's go ahead and separate it so it's a little bit more clear. So we'll look at the Z component or the T3 component. So T meaning translation, R meaning rotation. We see that we have a value of 0.17, which is aligned to the value that we see here, 0.17. So we've confirmed this. We whatever we see here, it's matching what we see here in the F06 file. Okay, I believe there was something else I wanted to cover. Right, okay, so let's go over one other thing. So if you remember, we define the solution frequencies with a frequency 1 and a frequency 4 entry. And then we use this plot to look at the excitation frequencies. And remember, I'm using forcing frequency, excitation frequency, and solution frequency to all mean the same thing. We see 20 hertz, 40 hertz, so on and so on, to 100 or 120 hertz. We then see 129, 131, 133, 135, 137, and 140. Those are the same solution frequencies that are listed in the frequency column. So let's go ahead and confirm. 20 hertz, 40 hertz, etc., 100 hertz, 120 hertz, 129, 131, 133, 135, 137, and then 140, 160. Those are the same ones we see here. So 137, 140, and then if we move this to the right, we should see 160. So this list of excitation frequencies, it's matching what we have here. Okay, one other thing. Again, we want to save our work. We want to send this to a colleague, a friend, another student. The professor will click on download PDF. And let's go and rename this file. So let me delete these old F06 files. And let me rename this. We'll call it C frequency response. And let's go ahead and open this, and let's go ahead and do a quick summary of what we did. We we defined our dynamic loads with the rload2 entries. We use a table D1 entry to define B of F. We then define a table for damping, and then here in the head of the file, the top part of the file, we said perform a SOL 111 or a modal frequency response analysis. Use the dynamic loads that we defined. So we define a deload command. It points, here it's a pointer. It's pointing to 9001. It's pointing to this entry, 9001. And then here we said output the data in the sort2 format, print it to the F06 file, output magnitude face values, and only output it for this list, 1. And here we have the list, a set 1. Output the displacements for nodes 2, 3, and 16. We performed the analysis. We then saw graphs in the HDF5 Explorer. Here, a few other things I forgot to mention. If you want to switch to the face term, you can switch and select ZP. If you want to look at the real term, you can select ZR or ZI, like you see here. If you want to switch to a different node, you can click on the other plot and it takes you to that node. Suppose you want to create a different plot for a custom node. Here you would deselect auto execute. Suppose you want to make a plot for a different node. Let's go ahead and select these two nodes. This is node 3 and 19. So here first I'll type in a node 3. I'll click acquire. And then here recently we've been having some stability issues with this web app. Let me show you how to recover from this. If you ever see this message, it helps to reopen the H5 file. So let's go ahead and reopen that real quick. So we'll go ahead and wait for this to load. I'm thinking that there might be a read permission issue. So here, let's try that again. We'll try and recover data for node 3, and you'll see that it works now. So there's definitely a bug in here somewhere where we'll have to go ahead and take a look at. So here, I've extracted displacement data for node 3. Click on create plot. Here at the navigation bar, that link blinks. Click on that. This is the new plot you just created for node 16. Let's suppose we want to create a plot for a node, 19. We'll click on acquire data set. Node 19 is not part of the data that was output. Remember that we're outputting data for node 2, 3, and 16. Since there's no data for node 19, we get this empty table. Look what happens when I say create a plot for node 16 or acquire the data for node 16. I now get data. I click on create plot. It creates a new plot for me, and in the plots browser, you get additional plots. So let me actually show you this again. Let me delete all of these plots. So you notice if you go to the plot section, it's empty. Let me delete the eigenvalue table too. So there are no plots. Let me create plots for node 2 and 16. Click acquire data set, click create plot, click on this link, last plot added, and now I get those displacements plotted on top of one another. I can look at the markers. I can look at the max-min labels. I can click on download CSV, and then I can go ahead and open this in Excel if I wanted to. So the goal, let me make sure I downloaded this. Yes, I did. The goal with this tool is to quickly get you the plots, because I know it's a very time-consuming process, but here we try and make the job as easy as possible for you. So let's go ahead and do this. Let's format the vertical axes. use the log format. Maybe we want to switch the chart type so we have lines between the points, so something like that. And then you can add some other labels. Let's actually add the labels. So remember the horizontal axes, that's going to be, how do I say? This is going to be the excitation frequency. I also call it the solution frequency, or you'll see it called the solution frequency or the forcing frequency. So this has many names. Know that they're all the same. And then here on the vertical axis, we'll go ahead and call this displacement, z component, and this is a magnitude. So there we have it. That's what we did today. Let's go ahead and see if we have anything else to share. So at this point, I believe we're done with the frequency response analysis, right? And let me see if there's anything to share, any other information to share. So at this point, you can stop the video here, and I'm going to go over a few other things. In this next topic, we're going to go over the scenario where you make your mesh in a different program. So let me show you what that is like. And let me see if I can do this here. Let's suppose we had this. Suppose you create your mesh in a different program. So it might look something like this. Maybe you're using Patron. Maybe you're using Hypermesh. Maybe you're using FEMAP. Maybe you're using MCApex. Maybe you're using some other mesher I don't know about. You can export the mesh to a file like you see here. And then we'll go ahead and call this maybe mesh. And now the question is, hey, how do I take that mesh? How do I configure it in the web app? So let's go ahead and open a different window and let's import that mesh. So whatever's inside of that bulk data file, that input file, that's going to be imported to the web app. So here you'll notice that if we open the pre panel, we go to open entry, we get a summary of what exists in the model. We see that we have a CQuad4, a grid, a mat1, and a P shell. So this is our mesh. Let's take this imported mesh that came from FEMAP, Hypermesh, Patron, MCApex. Let's go ahead and perform a Nastran analysis. So if you remember back from the video, we have to convert the weight, the mass matrix that's in weight units, we have to convert that to mass. So we'll go ahead and use this weight to mass conversion factor. And then we use the one option for the coupled mass option. So now we have two parameters. We configure this for a SOL 103 analysis. So let's go ahead and do that real quick. Let's go ahead and define our eigenvalue extraction method. So here I'll go ahead and say extract 15 modes. And then we have to define our support. So we'll look for SPC1. We'll click create entry. We'll go ahead and select some of these nodes. Let's go ahead and resize our picking sphere. We'll select these nodes on the edge. And just because we define the boundary condition doesn't mean Nastran's going to use it. So we'll go ahead and do this. We'll go to loads and BCs. And we'll assign SPC1 to the above subcase level. And then everything we do on the left, it's here on the right. And then we have to turn on the method command. And we're going to tell Nastran, hey, use that eigenvalue entry, where the eigenvalue entry says extract 15 modes. Also, we have to output the eigenvectors. So we'll do that with this option. And we'll click on reduce size of F06, just so the file is not too large. And then here we'll click on add HDF5 out. This is going to trigger the output of the results to the H5 file. Okay, so now we're looking at mode shapes. Let's go ahead and do this. Let's go ahead and adjust the scale factor. Let's go ahead and scale the mode shape a little lower, maybe 0.05. So this is mode shape 1, mode shape 2. So again, just because you created the mesh in a separate program doesn't mean you can't use the web app. You can use the web app. Simply take the bulk data file and import it to the web app, and now you can continue on with your work. Okay, one other thing. What happens if you get different answers? So what happens if you get different answers? So I wish somebody told me how to do this, because I spent hours trying to figure out where I went wrong with the tutorial. In some ways, that made me a better Nastran user. In another way, maybe I spent too much time on that. So this is what you do. Whenever you have a tutorial, they should provide the files from that tutorial. So here, this is the file that was used to create this PowerPoint. So let's go ahead and move it side by side. So let me go ahead and move, what's going on here? My program here is having a glitch. So let's move this to the other one. Okay. So this is the file from the solution files. Usually the company who made the tutorial provides these solution files for you. So if you don't have them, ask the company for the solution files. Then in this other window, I'm going to open the bulk data file that we created in the web app. So we're going to compare them now. Let's suppose, or for now, let's compare them. So we'll look down and we'll notice that there are a few differences. In the exercise, in the tutorial, they only outputted the displacement. There's no stress command. But when we did the exercise, we output the stress command. We used the byline option. We said output the stresses at the center and the corners of the element. We also said output the displacements, use the sort to option, and you output the magnitude and phase values. We use the phase describer. So when you compare this, you can use the result of the comparison to determine, okay, I think I might have made a difference here. I'll give you another example. Let's suppose that for now there was a 100% match. Let's suppose that when we did the exercise, we forgot a few things. We forgot to specify the Young's modulus, and we forgot to adjust the thickness. So we'll go ahead and change the Young's modulus and the thickness values. When we perform the comparison, we get told, hey, there are differences in the isotropic material. There are differences in the P-shell material. So if you carefully look at this, now I know the highlighting is a little confusing, but hopefully with time it makes more sense. Here we get told that this block of text is different before and then after. And then here, this block of text is different before and after. So this is a great way of telling where we deviated from the exercise. This is a great way of identifying why we get different solutions, because a lot of the time you look at a tutorial and they get a value, and then when you look at your results, you notice, hey, I got a completely different answer. Where did I go wrong in the exercise? So here, what you can do is just compare the known solution file with your solution file, and then look at the differences, and that will tell you a lot about where you went off the path when it came to the exercise. So I believe that was the last thing I wanted to leave you off with. Now, a few other things. If if you want access to the web app so you can practice your Nastran skills, you can visit theengineeringlab.com, click on the blue button, get access to the web app, and you can follow along. And if you do have a question, feel free to contact me at this email address. I would try and get back to you as soon as possible. With that, that's the end of the tutorial. And as always, thank you for watching.